Alright guys, so let's continue with the example that we were looking at yesterday, and we'll change things a little bit and look at the different ways that this question might be asked. So here we're given the function f of x is equal to x squared, and we want to find the area under the curve on the interval 1 to 5. And let's say that we're going to estimate this using 4 subintervals, so that would make n equal to 4. And we need to find delta x, and we said delta x is b minus a over n. In this case, b is 5, the beginning of our interval a is 1, and n is 4. So this will end up having subintervals of 1. So if we want to write out the area, remember that what we're going to do is we're going to split this up. So we'll have this be 2, 3, 4, and 5. We'll have to pick a method. Usually in the book it'll be specified. So let's pick the left endpoint method. So we're going to have an endpoint here. We're going to have an endpoint at 2. We're going to have an endpoint at 3. And we'll have an endpoint at 4. So this is probably going to underestimate, and we could have a more accurate answer if we tried more intervals, but we'll do this for now. Remember that each of the rectangles dimensions are given by delta x and the value of f of x evaluated at that point. So that first rectangle is going to be evaluated at 1, the next rectangle is going to be evaluated at 2, and so on. So our estimate for the area then is that the area is equal to delta x, which is 1, times f of x evaluated at 1, so that's going to be 1 squared, plus 1 times 2 squared, plus 1 times 3 squared, plus 1 times 4 squared. Okay, so now we need to evaluate this. We could do this by hand, but let me show you a trick that you can use with your calculator to make this a little bit less tedious. So the first thing that we can do is we can go into y equals, and the function that we're trying to evaluate is 1 times x squared, evaluated at a couple different points. So we can define a function y1 that's equal to x squared. And then in the home menu, we can write out our expression. So we'll press vars, y-vars function, select y1, and tell it to evaluate at 1. And then we keep doing that for the other points. So we'll press vars, y-vars function, y1, and we'll have it evaluate at 2. And 3. And then we need to do 4. So we'll press vars, y-vars function, y1, 4. And then we can press enter and it'll evaluate. So the estimate is 30. You can see that in the line above, the exact answer is 41 and a third. So like we thought, we got a bit of an underestimate. We didn't use very many subintervals, so it wasn't very accurate. Okay, so let's take the same function, but let's use the method of estimating with rectangles to find different things other than area. So if we were to take the curve f of x equals x squared, and we were to rotate it about the axis, it would create a shape that looks like this. And we could estimate different things about this shape, like its surface area or its volume, by splitting that shape up into subintervals and pretending that it was made out of disks that had different radiuses. We could estimate the surface area by taking just the surface area of each of the disks. And we could think of that as just being a ribbon that's wound up into a circular shape. We could find the volume of this shape by thinking of each of the disks as a cylinder, and so the volume of each cylinder would be pi r squared times the height, which would be delta x. And over here for the surface area, the expression for surface area would be the perimeter of the circle, 2 pi r, times the height, which is delta x. And again, notice that for both of these ideas, the radius of each disk is changing, and it's given by the function f of x that we were given, and that's how things are usually going to be. So we can get an estimate for the surface area of this shape, and we can get an estimate for the volume of this shape. Now, the volume of the shape is pretty straightforward, so we'll start with that. And if you followed along with my example in the last section, we can use our calculator to answer this question a little bit more quickly. So we still know we're going to have the same interval. Let's just say that we're going to use n equals 4. Our delta x is still going to be 5 minus 1 over 4, so it'll be 1. But in this case, our volume is going to be the sum of each of these cylinders. So instead of plugging in the volume of the area of a rectangle like we did in the first example, we're going to use the expression for the volume of a cylinder. And r squared is going to be our function. So the volume of the first cylinder will be pi 1 squared squared, since our function is x squared, times delta x, which is times 1. So the way that I got this is, again, pi r squared delta x. Delta x was equal to 1. R squared is equal to the square of our function, and our function is x squared. So we could keep writing out all of these expressions, or we could realize that we can use our calculator to solve this quickly. So what we're going to do is we're going to change our function. So instead of y1 being equal to x squared, we're going to say y1 is equal to pi times x to the fourth, since that's x squared squared, times delta x, which is 1. So we'll just leave it like that. So we'll press enter. We'll go back to the home screen. And in this case, because we haven't changed the subinterval or our interval a to b, and we're still using the left endpoint method, the points we're evaluating the function at won't change. So we can actually reuse this in our calculator. We don't have to type it again. And there we go. So our volume, after we type all of this in, or after we write all of this, pi 2 to the fourth plus pi 3 to the fourth plus pi 4 to the fourth, is equal to about 1,112. And that's a good estimate for the volume. We can do the same thing for the surface area. In this case, the surface area is given by 2 pi r delta x. And again, r is x squared, since that's our function, which gives the radius, and delta x is 1, based on the way we set up this problem. So we can plug that into the calculator. We're just going to change our expression for y1 now. It'll be 2 pi x squared times delta x, which is 1. So we have that. And we can go back to the home screen, get our expression again. And now we see it's about 188.5. Now, the surface area is a bit tricky because it depends on how the question was asked. In this case, we've only calculated the surface area of the side here. If they ask for the surface area of the volume, or they ask in some way indicating they want the total surface area, we need to go back and find the surface area of the ends. And in this case, that's not too bad to find because we know that the first circle had a radius of 1, and we know our last circle had a radius of 4. And that comes from the fact that in the previous problem we used our left endpoints and we started at 1 and went to 4. So to find the surface area, we don't need to use any calculus. We just need to find the area of a circle, since those two surfaces are just circles. So we can add to our answer pi r squared plus the other cap, pi r squared. And that would give us an answer if they had asked for the complete surface area of that shape. For the homework, if you go down just one page in OneNote, you'll see that I have two shapes that are similar to the shape that we just looked at, and similar questions as well. So try to use this video and the examples to answer the first question. And then the second question is a little bit tougher, but I've got a hint there for you. See if you can figure it out.